So, as was said, I work for Credit Suisse, and I work in the Quantitative Strategies group. And what I'm going to talk about today is a new framework that we use to create the next generation graphical tools that we're delivering to all of our users. And this framework is based on both F# and WPF, but I will spend most of my time talking about the F# part. And I have really few slides. I only have 7 slides. I only have information on 4 of them, and the rest of the time I will actually spend writing code. I like writing code, and I hope that you will like it as well. But before I start talking about the framework itself and writing code, I thought that it might be good to give a little bit of background to who I am and what I'm doing. So, as I said, I work in the Quantitative Strategies group, and what we are is a modeling and analysis team at Credit Suisse. And the things that we do is that we build all of the official models and tools that are being used to value trades. So that would be to look at the trades that we have on our books and then trying to figure out how much we have lost on these trades or how much money we've made. We also make all the tools and models for doing pricing. So that is something that the trader would use when a client calls up and says that I want to buy this or I want to sell this. Then they would use our pricers to actually figure out how much they should charge for it. And we also produce all the models and tools for evaluating risk and also doing analysis of the markets. And the way that we work is both that we implement all the models for all the existing trades, but we also work very closely with the trading desk. So it could be that a customer calls up a trader and says that, oh, I have this great idea of a product that I would like to buy from you, and we have no way of evaluating this. Then the trader would come with us, and they would get our help, and then we would create a new model. And we would also help them to analyze things like risk exposure. So the way we do it is that we use a number of programming languages. So traditionally, we've used a lot of C++. And nowadays, we tend to mostly use C++ for the more low-level components where performance is really crucial. So that would be if you have like an equation solver or a Monte Carlo simulator or something like that, then that would most likely be implemented in C++. Then we have a quite big layer of F# code that lives on top of the C++ code. And that is really, if you would go away and write a model for some kind of product, then you would use already existing C++ components, but all the new logic that kind of captures the new details about this trade would be implemented in F#. And F# is really great for that. So I really love Haskell, and Haskell is really good because you have all these nice things with rank 2 polymorphism, and you have type classes and everything like that. That doesn't exist in F#. But F# still has a lot of good features. So it's a functional language. You can write things in a functional way. It has algebraic data types. It has polymorphism. It has a lot of nice things. In a way, you can almost say that F# is like the slightly poor but also grown-up brother of Haskell. So you lose a lot of things, but it's a real language. You have support for it in Visual Studio. You have a good debugger. You have IntelliSense. You have all these tools that don't really exist for Haskell. And also, you have access to all of the libraries that exist on the .NET platform. So F# is really great. We also use Excel as our main UI platform. So we write analytics in C++ or in F#, but then the tool that the traders are actually using will most likely be an Excel spreadsheet. There is some C# code floating around as well, so we don't tend to use a lot of C#, but some of the other IT groups are using C# to interface with our code. And that is another great benefit of F#. So you can write a piece of F# code, you can call it from C#, they don't really know that we are using F#, and you can do it in another way as well. And then we have some legacy use of some proprietary languages, something called Paradise that Lennart was part of. That is now deprecated. We have some other languages like PDC2, that is a language for writing Monte Carlo scripts. So we also have that floating around. So back to Eden. So what kind of started Eden was that we had a project that was running before Eden that was called Paradise. Hence the name Paradise and Eden. They're quite similar. So what we did was that we use Excel as the UI platform, but it's very difficult to write complicated spreadsheets. So therefore, we wanted to have a more high-level language where you could kind of describe the prices that you wanted to have, and then it would automatically generate the spreadsheet for you. And that was essentially what Paradise was. And Paradise was a DSL embedded in Haskell. And Paradise was really great, and it's a great idea, and it was implemented in a really good way. The problem with Paradise is that Excel isn't really a good platform for creating user interfaces, and it is not a very good calculation engine. It's a little bit slow, and there are a lot of problems with it. So we want to move away from Excel. And two of the reasons is that we want to be able to create much richer user interfaces. And one of the problems, and especially more dynamic, and one of the problems with Excel is that it's essentially a two-dimensional grid. You can lay out some controls, it works quite well, and it's good with Excel as well because all the spreadsheets, they look the same. But if you want to have something like a tab controller, you want to have docking windows, or you have something like that, then it's extremely difficult to do it, not to say impossible to do it in Excel. And even though you can have some things that are dynamic, you can insert new rows, you can insert new columns, then Excel is very slow at doing that. So it just doesn't really work. It has worked for a surprisingly long time, and I couldn't really believe it when I joined Credit Suisse 5 years ago. And to kind of see the scale at which we use Excel, it's amazing. But now we've kind of reached the limit. And then the second reason that we want to move away from Excel is that even though you can do things, and it was said yesterday by Simon Payne-Jones, I think, saying that Excel is really functional programming language. It's a quite simple programming language, but still it is a programming language and it's functional. But it doesn't have any support for structuring the code, and you can't really create functions. So we've extended Excel so you can actually write Lambda functions inside the spreadsheet, but still, you don't really have any structure. You can only use kind of conventions saying that maybe the input should be in the top left corner, the calculation should happen on a different tab and so on. But if you've seen a spreadsheet with thousands and thousands of cells spread everywhere and you have strange formulas and you have a lot of data dependencies, then it's very difficult to debug it. It's very difficult to understand how it's working, and hence it's very, very difficult to maintain it. It's also very difficult to share functionality between different spreadsheets. So this is essentially what we wanted to do. Then we said that we need to start from scratch now, and we need to kind of look at what requirements we had. And we came up with a list, and we can group them in three parts. The first part is around what kind of calculations that we need to do and how we need to be able to do it. So first, we want this engine to be lazy, and we want to have support for partial recalculation. So that would be that you have a pricer that has that is evaluated a trade, then the market changes a little bit, then we need to go away and re-evaluate the price. But we don't want to change the things that didn't depend on the change in the market. So we want to be clever. We also want to have support for caching. It's really important that we can produce things asynchronously. So we want to use this engine to create new user interfaces, and you should never lock the user interface. So traders, they are quite vocal. If a trader doesn't like anything, then they're going to complain about it. And the UI blocking, they will definitely complain about it. And since the traders are the one making money, that means that you need to actually fix it as well. Then another thing that is a bit unusual about our bank, and I would guess most banks in general, is that the modelers, who are actually the ones writing the code, they're not computer scientists. They're not really programmers. They tend to have a PhD in math or in physics, and they're really math guys. They know how to write the model, kind of the math model, and kind of figure out how to evaluate the price, but they can't really write code. And we are in a situation now where we have a lot of machines that are very fast, and a typical trader machine, it has like 8 cores or so, and a lot of memory. And we want to make use of all these cores, but we can't tell our modelers to go away and figure out how to write multi-threaded code. So we want the framework to do it as much as possible for them. The manual calculation, so what we want to have is that we want to have a user interface where values are just ticking. So as the market is changing, then you get new prices and things are just flashing. Traders like that. But sometimes, if a calculation is really slow, then we want to have some way for the trader to say that don't evaluate this result automatically, but only do it when I tell you to, like pressing a button or so. So we want to have a difference between things that are constantly flowing through the system and things that are evaluated more by demand. And finally, we also want to have support for cancellation. So imagine that the trader is entering some data. He has a client on the phone. He starts the evaluation, and then the client says that, oh, no, I actually wanted to do this instead. That we don't want the trade to be forced to wait for a minute or so to get the result and then start another calculation. We want to be able to instantly abort everything that is happening, make a change, and then restart it. So all of these together led us to base the framework on a dependency graph. I will just draw a small picture here to show you what I mean. So I'm not sure if you can all see this, but what we have here is that we're going to have nodes, and we might have some nodes that are input nodes. I will see. This one. Is it better? Yeah, perfect. So we have a few input nodes. Then we're going to have some nodes that are going to depend on these inputs. So it might look something like that. Then we're going to have other nodes that depend on these in turn. And then finally, we might have some output node. So it's almost like you can imagine that these are, if you take a function, then the arguments to the function, that would be turned into input nodes. The result of the function, that would be a final output node, and all the intermediate calculation will be captured inside nodes here. So each node here is going to contain a function that takes the value of the dependencies, applies the function, produces some results, which will then be consumed by the nodes further down. So we want to be able to express all of our calculations in terms of a graph. And then what we want to do on the UI side is that we want to, for example, have a text box here connected to an input node, another text box here connected to that input node, and then some box down here that is connected to this one. So then the idea is that inside the user interface, the user or the trader enters a value here. It's going to change the value to input node. It will kind of flow through the calculation graph, and then we're going to get a new result that will just pop up in the user interface. So this is what we want to do. Another requirement, and also one of the kind of bad things with the previous framework that was based on Haskell, is that it was very clever. You wrote Haskell code, it generated some other Haskell code, you ran that, and it generated some VBA code and a spreadsheet, and then you ran the VBA code, and then you got the spreadsheet. And it was working really beautifully. The problem, though, is that when you had a bug in the generated spreadsheet, and it had like hundreds of thousands of cells with random things, then you had no way of kind of connecting this broken formula in a particular cell in the spreadsheet back to a line in the Haskell code. That was extremely difficult to do. So it was more or less impossible to debug these spreadsheets. So in a way, this is a counteraction to that. So we want to make sure that the code that the modelers are writing in the new framework is exactly the code that gets executed when they run the model. And for that reason, we decided to base everything on F# and have a kind of direct F# implementation. So that means that a modeler that writes a model in the new framework can use all the normal tools that are available in Visual Studio. You can use the debugger, and it just works in the normal way. And then finally, we wanted to have access to a wide selection of UI controls, and we also wanted to have a separation between the logic that we're implementing and the view. And the reason for that is that we can implement the logic once, and then we can have a view that is like a normal Windows application. We could have something that is web-based, or we could have another system that is consuming our logic. And then in order to achieve that, we decided to use WPF, which is a Windows presentation framework, I think. And then we're making extensive use of the model view model pattern. And what this pattern is giving us is essentially that the way that you can connect a text box to a node here is almost like using message passing. So if you change the value in the user interface, then it will send a message to this node. Then it's going to kind of flow through the value, and then this backend, or the view model, is going to send a message to the UI saying that now you need to go away and update yourself. So you can kind of think about this as message passing, and I will come back to that a little bit later. So, time for a demo, and now I have only one more slide that contains information, and I'm going to write code instead. So, what I will do is that I will implement a simple version of the calculation graph. So it won't have all of the features that we have in our real production graph, but then I'm going to do this in half an hour, and it took me like a year to write the real calculation graph, so that would be a bit strange if I could reproduce it. But most of the important features I'm going to cover today, so there will be a lot of kind of slightly boring technical things that will not be covered. So let's get started. Oh, and by the way, if you don't know F#, then this might be a good introduction as well. And I really like F#, so hopefully you will do soon as well. So the first thing I will do is that I will create a type for a node. And I'm going to say that the node is either an input node, and if it's an input node, then it's going to consist of an integer reference. And you can think about a reference as a container of something that is mutable. So that means that you can look inside the container, you can extract the value, but you can also change the value. So like Haskell, F# is immutable by default. So if I would just say that an input node has an integer, then that's it, we can never change it. But we actually want to change things here. Then I'm also going to say that a node could be an output node. And to simplify things here, I'm going to say that each output node always depends, or always have two nodes as its dependencies. And then finally, it's also going to have a function that takes two integers, and then it's going to produce the result. So a very, very simple data type. So I'm going to select it, and I'm going to send it to F# Interactive, which is down here. So this is a bit like a GHCI, so it's a REPL. And compared to C#, so this is going to come for C# as well in the new version of Visual Studio, but you don't have it yet for C#. And this is really good for your productivity. So compared to having to write all the code and then executing it, or compiling it and then executing it, that is very, very slow. And it's also very difficult to run exactly the new code that you've written. Compared to just writing the code, copying it down here, then immediately it gets interpreted. That's really great. So we also want to have an evaluate method that takes a node, and then it's going to return the value of the node. So what I'm going to do is that I'm going to inspect the node to see what kind of node it is, and it's either an input node, and if it's an input node, then I'm going to bind R there to the reference, and then we already know that we don't really need to do anything in order to evaluate this node, so I just immediately return the value of the reference. So, and this is not a great thing with F# and the integration in Visual Studio. So you already see here that I get these squiggly marks here. And then IntelliSense is able to tell me that, oh, I know that the node type is either an input node or an output node, and you haven't covered all of the cases. So it's really good, and it even tells me which case I missed as well. So if it's an output node, then I'm going to bind to the two nodes, N1 and N2. I'm going to evaluate them. And then finally, I'm going to apply the function to the values V1 and V2. And now you notice here that we get these red squiggles here, and it's saying that the evaluate symbol isn't defined. And the reason for that is that by default, functions are not recursive in F#. So if you want to be able to call it recursively, you need to also put the rec keyword there. So let's take this and copy to FSI. So you see that it compiled fine, and eval is now a function that takes a node and returns an integer. So I also want to have a function that allows me to change the value of a node. So it's going to take a node and a value as arguments. As before, we are going to inspect this node. So if it's an input node here, then we're going to get the reference, and now we're going to update the reference. And you do that with a colon equal. So that will overwrite the previous value. And otherwise, it's going to be an output node. I don't really care about the components. I just use the underscore pattern match. And then what we'll do here is that we're going to fail. Cannot set the value of output node. So like that. And we can send this to FSI, and it works. So now I'm very soon done with the first version of this calculation graph. So I need to have ways of constructing these input nodes. Well, I don't really need to, because I could construct the nodes directly by using the input and output case, but I will make some changes to this later. So I will create an API that kind of abstracts over this. So input here is going to take an initial value, and it's going to create an input node that contains a reference with the initial value I. So let's send that, and you can see that it takes an integer and returns a node. For function nodes or output nodes, I'm going to take the two nodes that they depend on, and I'm going to take the function, send that to FSI, and it seems to work. Perfect. So let's create some nodes. So I'm going to create a few input nodes. So I1, I2, and I3, like that. So you can see there are all nodes. I'm going to create 2 function nodes. So this is going to depend on the first 2. And here I'm using lambda abstraction. So the function is going to take the 2 values it's given, and then it's just going to return the sum of the 2 functions. But before it does that, I'm also going to make sure that it prints something out on the console so we can actually see that it's evaluating. So it's going to evaluate N1, and then make another one. Let's call it N2. And so like that. And let's send these to FSI. And now we can go away and we can evaluate N1. And as you see here, it printed out eval N1, so it has actually run this function, and we get back the result 3, which is indeed what we were expecting. And we can do the same for N2 here, and you see that it applies a function. We can change the value of I1 to 100, and then we can evaluate N1 again. And you can see that we get the new value. So this is already quite good. So we have something that we can almost connect to a user interface now. We can use, whenever the user changes something in the UI, we can call the setValue function, and that will change the input node. And we already have lazy evaluation because nothing is actually evaluating in the graph before or until the UI actually asks for the value. But we have 2 problems. So the first is that how does the UI know that it has to request a new value? We could set it up in such a way that as soon as the user makes a change, then we go away and we evaluate all of the nodes that are being bound in the UI, but that might be quite slow. So we want to have some way of kind of tracking the changes and notifying the UI that some of the results might have changed. And another thing that we don't have support for either, which will be apparent if I evaluate N2 here, is that none of the dependencies of N2 has changed. But if I evaluate N2 again, then you can see here that it's still going to apply the function. So it's not keeping track of what needs to be recalculated and what doesn't. And in order to solve both of these problems, I'm going to track dirtiness. And by dirtiness, I mean that if the value of this input node is changed, then it's going to trigger an event, and that will make sure that all nodes that depend on this node will be flagged as being dirty. And dirty means that they might potentially have changed a value. And I'm going to do this recursively. So the entire kind of transitive closure of all of the forward dependencies of input will now be flagged as dirty. And whenever a node is being flagged as dirty, this will then send a message to the UI saying that there might be a new value, and you might be interested in requesting that value. And then the UI can go away and see if the text box that is connected to this node is visible, then the user might care about the new value, and then it can then request the new value. So let's make that change. So I'm going to add an event to the input node. So it's just going to be a normal event, and this is an event that will get triggered as soon as the value changes. For an output node, we need to do a little bit more. We need to remember the previous value. Otherwise, because every time we evaluate a node, we need to return the result, but previously we never remembered the results. So we're going to have a reference that is the last value. We also need to have a reference for a Boolean that tells whether the node is dirty or not. And then finally, we need to have the dirty event. So let's send this to FSI, and that works. So now in the evaluate function here, we need to add the event to the pattern match for the input node, but we don't really care about the event, so we're not going to do anything. Here, though, we need to bind to the last value. We want to bind to dirty. I don't really care about the event. We're then going to see if the node is dirty. And if the node is dirty, then we will go away and we will evaluate the 2 nodes. We are going to apply the function, and we are going to update the last value. And we also need to remember that we should set the dirty flag to false. And then, finally, we are going to return the value of the last value. So you can see here that if the node is not dirty when we enter the eval function, then we will immediately jump down to that line, and then we're just going to return the current value of the node. So let's copy this to FSI. So when we set the value for an input node, then we need to make sure that not only do we update the reference, but also that we trigger the dirty event. So we just do that by calling the trigger method on the event itself. We can send that to FSI. So when constructing an input node, we need to construct the event. We don't really need to do anything special here because it's always the listeners that need to set up the event, so we just need to create one here. We can send this to FSI. For a function node, though, it gets a little bit more difficult. So first we need to create the reference that holds on to the current value. And now I'm just going to say that all nodes are going to be created with 0 as the initial value. That doesn't really matter, because as soon as you ask for the value, then it will immediately go away and re-evaluate it. And I'm also going to have the dirty flag. And we need to make sure that all the output nodes are dirty when they are created. And also we need to create our event here. So like that. So now I can stick these things in here, dirty and the event. And this should work. Perfect, so I can even send this to FSI as well. But now I've forgotten something, and that is that I need to make sure that the dirtiness of this function node is linked to the dirtiness of the dependencies. And in order to do so, I first need to write a function called getEvent that will take a node, and this is going to be the dependencies, and then it's going to return the dirty event of these nodes. So I'm going to match a node. If it's an input node, then I want to return the second component. If it's an output node, then I want to skip the first two that are dependencies, the function, the less value, the dirty flag, and then the event. So if I move the mouse over getEvent here, you can see that it takes a node and then it's going to return the event. And this is the event that we need to listen to. So I'm going to call getEvent on N1. In order to listen to event, we need to first publish it. Then we can add a handler. And what we're going to do in here is that we're going to set our dirty flag to true. And then we need to make sure that every node that depends on this node is also dirty. And we do that by actually triggering our own dirty event. So like that. And I need to copy this and do the same for the second dependency. And this should be it. So let's send this to FSI. So that seems to work. I can now recreate the input nodes, recreate the function nodes. I'm going to do the same. I evaluate these. You can see that they are evaluating. They give the right results. I evaluate N1 here. And now the moment of truth. It didn't work. That was a bit. Let's evaluate it again. Oh, okay, I just forgot to evaluate. So the first time we evaluate N2, then it's going to be dirty. The second time we evaluate it, nothing will happen. So it will just return the previous value, unless we, of course, change the value of one of the dependencies. So if we would set this to 44, for example, and then we would evaluate N2, then you will see that it actually goes away and evaluates the node. So this is actually quite cool. So how many lines of code do we have now? We have 36 lines of code. And in 36 lines of code, we have something that you can actually use to write a rather modern UI using WPF, and you can connect more or less directly to the graph. So one thing that is still a bit bad with this is that you can change the value here. It will change the value of the input node. It's going to propagate dirtiness, and it's going to notify the UI that there is a new value. You might be interested in requesting it. But as soon as the UI is going to request the value, then it will be blocked, because it will then go away and evaluate all the dirty dependencies until it gets back. And in this example, it's quite quick to do so, because we have a very shallow graph, and also the functions that we're executing inside the nodes, they're very quick. But imagine that one of these is going off to a farm and doing crazy stuff, and it takes like minutes, then the UI is going to be blocked for a long time. So we want to make sure that all of this is happening asynchronously. So the way that we want this to work is that this node here is going to send a message saying that I'm dirty, then this text box here, if it's interested in the value, then we want it to send back a message saying evaluate. And then this will just go away and evaluate in the background. And then when it has a new value, it will send a new message to the UI control saying, OK, I'm done, and here is the value. And this can be a bit difficult to do. So it was one of the people in the Erlang presentation today saying that if you have something that is asynchronous, it's very easy to make it synchronous. But if you have something that is synchronous, then it's very, very difficult to make it asynchronous. And everything so far in our code is synchronous. So now we need to somehow make it asynchronous. And that isn't at all as difficult as you might think it is. And the reason for that is that F# has something that is called workflows. And a workflow, or a computation builder, or a computation expression that is also known as, is very similar to a monad in Haskell. And that kind of allows you to write code that looks like normal code, but that will kind of be lifted into some other domain, and there will be magic happening. And in the async workflow, the magic that is happening is that all of the code will all of a sudden be asynchronous. So that is what I'm going to do now. So we don't need to make any changes to the node type itself. It's perfectly fine. The only thing that we need to change is the evaluate function. So what I'm going to say here is that it's, instead of returning an integer, it's now going to return something of type async int. And async is a computation or a calculation that can be executed in an asynchronous way. And when it's done, it's going to give you an integer. The way that you turn a piece of normal synchronous code into asynchronous code is by using the async keyword, and then everything that is within the curly braces will automatically be turned into something asynchronous. Now, in the case of the input node, there is nothing really to do, so what we're going to do is that we're just going to return the value. And if you wonder, then this return here is the same as the return in an Haskell monad. So I'm going to do the same with this guy down here. So let me indent it. So we know that down here, instead of just having the value, we need to return it. And now we can see here that we have a type problem. And here is saying that the function f here, it expects something of type integer, but instead is being given an async int, which is a computation that would give you an integer if you were to execute it. And that is a bit of a problem. And we don't really want to, so we can certainly take that eval n1 there, and then we could start running it. But the problem is that if we start running it and we do it in a blocking fashion, then this code will still be blocking. Even though we are running this thing asynchronously, the rest of the code is kind of sitting there waiting and is blocking the thread. But that is where we can use some of the magic in the async workflow. So instead we're going to use something that is called letBang. And what letBang will do is that it will look at all the code after the right-hand side here, eval n1. It will turn all of this code into a continuation. And then it's going to evaluate n1. And it will do that on the background. And it's going to give the continuation to the evaluate n1 function. So that means that there is actually nothing blocking here. If you would call this, then it would immediately return, but you would have something that is in the background evaluating n1. And as soon as it's done with that, it's going to continue running this code, which will again do the same trick for this evaluate n2. So with very little changes to this code, we have been able to make it completely asynchronous. So now I send that to FSI. I'm going to, OK, I'm slightly running out of time. So I'm going to recreate these nodes. Now, if I evaluate the node now, you see that I get back something that is asynchronous. It's not an integer that we were expecting. So I need to create a new function, eval async. We are going to take a node here. And what I'm going to do is that I'm going to evaluate the node. And then I'm going to print out got a value, v here, so like that. And then finally what I'm going to do is that I'm going to start this on a background thread. So let's send this to FSI. So eval have eval async here. And now what you should be able to see is that I made the call here. It immediately returned unit. So that means that the thread of FSI is not being blocked. And then after a while, it went away and it started evaluating the node. And then finally, it got the value 3. So this is pretty cool. So now we can, using this implementation, we can actually support this interface here that it tells the UI when something is dirty. The UI can request the value, and a little bit later, it will then get an update saying that I've gotten a new value. So this is all good. But I also said that we wanted to have support for running things in parallel. And one of the great things with having a calculation graph in this way is that if we make sure that all of the functions inside the node are free from side effects, then it means that we can actually evaluate all of the nodes in parallel. So this node here can start evaluating these two children in parallel, and nothing can go wrong. The only thing that can go wrong, if you're not a bit careful, is that if these two nodes would have a common dependency, then you don't want to start evaluating these twice. You want to be able to actually share computation. And that is one of the things that are a little bit tricky to get right. And that we have in the real calculation graph, but I won't show you how to do that today. So I'm just going to create a naive thing, and I will update these things to print out the thread. And that should be system threading, thread, current thread, and the manage ID. Perfect. So I'm going to recreate these. Let's recreate that one. Oh yeah, and I'm going to create another node, N3 here, that depends on N1 and N2, just so we can see that it's doing its magic. So I will send it there, and then I'm going to evaluate N3 here. And as you can see, everything is running synchronously, and it's running on the same thread. So, but this is very, very simple to address. So the F-sharp async workflow has something that allows you to give it asynchronous computation, and it will automatically run them in parallel. And you do that by using something called async.parallel. So as you can see from the type here, it takes a sequence of async stuff, and it will give you back a single async that has an array with all of the results. So what I will do here is that I will tell it to evaluate N1 and N2 in parallel. It's going to return an array with the values. Instead of using V1 and V2, I'm going to extract the values from the array. And that is all the change we need to do in order to run all of these in parallel. And if you wonder where they're going to be run, then the async workflow is using the .NET thread pool. So all of these will be run in the background, and it's going to manage all the threads for you. So we can change these things, and now evaluate N3. And as you can see here, they're clearly being run in parallel. So we started evaluating N1 here. It started writing out the thread ID, but then in the middle, the second node started running. It was running on thread 7. So the first node was being evaluated on thread 6, and then the third node got evaluated on thread 6. So here we have it. And how many lines do we have now? So we have 37 lines of code. And now we have something that you can just take this, you can connect it to WPF, and you have a very good engine for actually running these calculations. So that is actually very, very cool. I will just spend a minute to show you a small demo. So I'm just going to add some stuff to FSI. Then all of this code is essentially what I've just shown you, but it actually implements the protocol that you need in order to drive WPF. Then I'm going to add some input nodes, some function nodes. I have an object that can visualize these graphs. I will add it to window, and then I will start an application. So let me see. So we probably want to lay this out. Okay, so whatever, I can make it a little bit bigger. So what we have here is that all of these things, they are input nodes. These things are calculation nodes or function nodes, and they are red now because they are dirty. And you can see that the initial value is 0. When I press the calculate button here, you can see that how it goes away and it starts evaluating all of these nodes in parallel. And just to show you that it actually does work, I will change the value of here. And now you can see how they are getting dirty. I will change this as well. I will start calculate, and I will move the window to show you that it's not blocking. So there we go. It can easily be done. And now back to my slides. So I have only one more slide here. So, and I thought that I should tell you a little bit of what works with this framework and what doesn't really work. And we've been using this framework for 2.5 years now, and we've actually used it to implement some pretty big applications. So we have one application that we have been around 4 to 6 people working on it for up to 2 years. So that is a lot of man-years that are going into that application. And that application is replacing some of the biggest and most nasty and horrible spreadsheets that we have at the bank. They were just too big. So in Excel, it's difficult to use more than 3 GB of memory, and these very often did so. So we have re-implemented that in the new framework. The UI is very well received by the users. That is actually a bit of a problem because now when we can do everything, that means that they will ask for everything as well. The responsiveness and the performance have generally been very, very good. And when you run one of our applications, you have these 8 cores, and you see how it just goes up to 100% on the CPU, and it uses all of the cores. That's actually quite cool. And you don't need to do anything in order to get something that runs in parallel. So you don't need to think about anything. There are no logs. There's nothing that can go wrong if you're a modeler. And it's also quite cool because it means that we can essentially get features like undo, redo. So unlimited undo, redo, we essentially get for free because we just have a graph here. So if the user makes any difference, we just need to keep a log of all the changes that have been made to an input node. And if you want to undo something, then we just unroll that log. And it also works with having a button that runs some arbitrary command because we just record the changes that the command is doing to the graph, and then we just unroll it. We also have automatic support for persistence, so you can run our tool, and at any point you can just save down the state to a file. So essentially what we do is that we just need to save all the values for the input nodes. We're actually saving down some of the output nodes as well, so we can use it for regression testing. But essentially we just save down all the values of the input nodes to file. Then you close the application, you open the application, you load back the state, and everything is exactly like it was when you closed the application. So that is pretty cool. So the things that could be improved. So the first thing is that everything would break if you start having functions that have side effects. So that means that you really need to program without having side effects, and that can be a little bit difficult for some people. It's a little bit difficult in the beginning, but then you start getting a little bit more used to it. But then the second point, unfortunately, sometimes you need to have side effects. It could be that you have 2 nodes that are kind of giving you different views of the same thing, or you have something that is a bit like an equation, so changing the value of one node should have the effect that you change the value of another input node. So what we've done there is that we kind of realized that we do have some need for side effects, and then we have added support for it in our graph, so we kind of give you a little bit of freedom to have some side effects, but it's strictly controlled, and you can only do it in the way that we allow you to do it. And then another problem is that, and this is not really anything that is specific to our framework, but once you start writing asynchronous and heavily parallelized code, then it's very difficult to debug it. So even though you can use a debugger, then most likely you will not be in a situation where you have 500 calculations running at the same time on different threads, and you're not really sure how exactly they relate to each other. And the final point is that as long as you kind of stay inside our framework and use our graph and use the controls in WPF and use our kind of protocol for sending values back and forth, then everything is really great and beautiful. If you try to do something that we don't really support, then that will be a little bit painful. And that was really the end. So, any questions?
So, a new question, to be honest. I'm not one of those Microsoft posers, but I'm not married to Microsoft yet either. So how easy would it be to run something like this on Mono on another platform than Windows?
So if you asked me that a couple of weeks ago, I would say that it was extremely difficult because Mono seemed to be dead. But I know that they just released a new version. And to be honest, I don't really know. We are quite heavily married to Microsoft, so I've never looked at Mono or so. But there's nothing in here that is really I would say, .NET specific or even F# specific in a way. The async workflow, you can easily write it in Haskell. You could do it in most other languages, I think. We rely on the thread pool being quite good at kind of creating and destroying threads, but otherwise you can take this idea and implement it in your favorite language quite easily, I would think. And it works as well.
My thanks to Tobias there. Clearly the demo gods were with you. I mean, it's a brave man who not only demos but codes on the fly and draws. So thanks very much for an interesting session. Again, folks, if you could register your feedback on the way out, greatly appreciated. Thank you. I don't know what.